Welcome back, ladies and gentlemen. So, as we discussed last time, boiling versus evaporation, there's two different things you're dealing with. You have to deal with the strength of the intermolecular forces and the strength of the air pressure pushing down. We can't change the IMFs, but as a result of that, the IMFs can be measured. The IMFs, the intermolecular forces, are material dependent. Depending on the material, those IMFs are fixed. They're constant. They're always the same. So I can map them because they don't change. I can't map the pressure because it changes all the time, but I can map the forces. So let's remember, right? When the vapor and the atmospheric pressures are equal, the liquid will boil. So anything less and the liquid will not. Okay, so that's the first step of this. We need to keep that in mind. If the pressure pushing up equals the pressure pushing down, then the liquid will turn into a gas. If the pressure going down is bigger, it'll stay a liquid. If the pressure going up is bigger, then it will turn into a gas faster. But the key is when they're equal to each other, right? When this tug of war is the same, then the vapor is starting to win. So what's this graph trying to show us? Well, water needs 100 degrees of energy to have its vapor pressure equal the atmospheric pressure, 101.3. Okay, well, down here on the x-axis, I've got the temperature. Okay, so down here we got 0 degrees Celsius. Here's 20, 40, 60, 80, 100. So here's 100. Now there's 4 different lines on here. Water is the blue line. So at 100 degrees Celsius, if I look up here and I read up here, I see that this blue line crosses this horizontal line. Well, what's this horizontal line? I read it back across to find the pressure, and it says that it's 101.3. Well, that's 1 atmosphere. That is the pressure of the Earth's atmosphere at sea level, which is where we are right now. So at 100 degrees Celsius, the intermolecular forces will map out this curve going up in the blue line. And once I hit here, where the blue line crosses this solid line, I boil. Now the shape of that curve is the same. It never changes because water is always water, right? Water has hydrogen bonds, very strong intermolecular force. They're not going to give up very easily. The strength of that stays the same. You can look on either side. We've got acetic acid in purple, we've got ethanol in green, and then chloroform in red. These ones have different curves because they have different types of intermolecular forces. When I cross the line at the top, that's when I boil. So look, there, right there, that is when chloroform boils. What pressure is that? It's always the same pressure every time because that's atmospheric pressure. But what temperature is that? I read down and I see here that it's going to be 60. 60. So it boils sooner than water. So it must have weaker intermolecular forces. Okay, well, if water is hydrogen bonding, maybe chloroform is just dipole-dipole. Right? That seems reasonable. It's weaker. I mean, maybe it's all the way to London dispersion. I don't know. It depends on what the structure of chloroform is. If we take a look at acetic acid, it boils at like 120. So is that stronger? I guess so. But is it stronger than hydrogen bond? Well, probably not. It's probably just a really strong hydrogen bond. Or maybe acetic acid has a very large structure. So the combination of hydrogen bonding and London dispersion, remember those two can stack, might be a little bit more than water. Or maybe it's just really heavy, so it's harder for it to boil, right? Because it's heavier, so it's harder for it to escape. Either way, when the curved line touches that flat line, that's when boiling happens. And the shape of these curves totally depends on the material itself. Each material has its own curve, its own shape. It's always the same for that material. So at that spot right there, water boils. Chloroform only needs 60 degrees because that's where it reaches, right? That's the spot right there. So there are only 2 ways to affect the boiling point of a substance. Notice I say boiling point, not intermolecular force. We can't change that. The intermolecular forces are fixed. The shape of this line is always the same. So there's only two ways that I can change the boiling point. What was the definition of boiling point? The boiling point is when the vapor pressure equals the atmospheric pressure. Right? It doesn't mention intermolecular forces in there at all. There's no mention of intermolecular forces. All I say is the vapor pressure must equal the gas pressure or the atmospheric pressure. Well, there's only two things I can change in that equation. The vapor pressure or the gas pressure. That's it. Those are the only two things I'm talking about. Well, how do I change the vapor pressure? I give it more energy. I increase the temperature. How do I change the gas pressure? I add more gas or take it away. That's it. Those are the only two options. How does that look on the graph? Change the temperature. So instead of having a temperature of 50 degrees, I make it hotter. I go to 60 degrees, right? That changes the vapor pressure. That changes how much energy the liquid has to work with. That's option one. Option two, this one's always the weird one, change the atmospheric pressure, change the gas pressure. I take the pressure and maybe I reduce it. Maybe I take away some of the gas. Maybe I get like a big vacuum on top and I suck away the gas. Well, what happens is there's less pressure above, there's less people hanging around the door. I lower this line that I have to meet. When the two meet, I boil. So I can either increase the temperature to make it so I get closer to the line up here, or I lower the whole line down so that way it lines up at this pressure right here, or this pressure temperature right here. Either one would work because that's the definition. There's only two variables for me to work with. I make the vapor pressure bigger, or I make the gas pressure smaller. Both of those we should do the same thing because I got to make the two of them meet, right? So if one of them starts here and the other one starts here, I can either bring this one up or I can bring this one down. When they meet, boiling happens. That's it. That's all we have to do. At this point, I would usually pull out a bell jar. I don't have one anymore. It got broken. So I'm going to try to track down a video for you guys to see this. The net result is that I can take my glass of water and I can make it boil at room temperature by taking all of the air out of the jar. If I have no air above the water vapor can escape easy, no problem, right? Because again, I boil when the two of them are equal. And I can either bring this one up, raise the temperature, or I can bring this one down, lower the pressure, get rid of the air, get rid of the kids in front of the door. So I'll find a video of that for you guys to see it. There's tons on the internet. At this point, you guys have got to do some more practice. And at this point, we're done. That's it. That is the rest of physical properties of matter. And at this point, you guys are going to be able to get ready for your unit test. And we're going to be able to start working on the gas unit, where we're going to look into the whole pressure thing in a little more detail. I hope all of that was pretty straightforward. I hope you guys were able to understand that without too much trouble. As always, if you guys have questions, feel free to ask me. I'm more than happy to help out. But otherwise, I will see you guys next time.